Hello, Professor Roberts and possibly Max. You have come to my OChem final project video. Today I'm going to describe how exactly this model I have made helps us better visualize the Wittig Olefination reaction than other models we might have. The first thing you'll notice is that this is very similar to a ball and stick model because the Wittig Olefination is a three-dimensional reaction, meaning we need 3 dimensions to understand it. My mind was instantly drawn to the ball and stick models. However, this piece has a few key differences that will help us understand the Wittig Olefination specifically in a better light and help us better visualize those transition states. Before we get going, I'm going to go ahead and label the parts of this molecule so that we're not completely lost when I start my demonstration. First off, this yellow piece here represents the phosphorus, whereas this bar here represents the extra pair of electrons given to the ylid. This right here is our carbanion. This little node represents that. These two large orbs represent R groups. In a ball and stick model, they would typically represent just a single atom. However, for this, we're going to say they represent R groups with a large and small R group. Here we have the carbonyl functional group. It has the carbon center, the electrophilic carbon center, This piece right here is typically where we're going to see the beginnings of the differences between my model and a ball and stick model. First off, these two parallel lines represent a double bond. Since it's pointed towards this carbon, we know this carbon has 1, 2, 3, 4 bonds. And so this is going to help us better visualize because the ability that we have to quickly move this up and down is going to help us see these transition states and how these molecules first attack. So let's go ahead and do the demonstration. First off, we have our attacking molecule, the phosphorus carbanion ylid. And this molecule is going to attack in a way to avoid the steric interactions. There are 3 phenols attached to this phosphorus in the Wittig Olefination. So it's going to go ahead and avoid this larger R group we have right here represented by the wheel with the tire. And so it's going to attack in this fashion, very similar to what we would see in a Newman projection. However, now we have it in 3D and are going to be able to better transcribe it. Because I've attacked this carbon, this must come up representing a negative charge on the oxygen. Because it is not attached to this carbon, obviously it comes up, and this straight line would then represent the negative charge on the oxygen as it did here with the carbon. However, we know that it's not going to remain in this transition state. It could reverse and go back here with this molecule once again becoming a carbonyl. However, we're going to go ahead and assume that the reaction moves forward. The way to do that is just pull this out really quick and just rotate it about this point until the two are lined up. Once they are lined up, these electrons are going to attack the positively charged phosphorus. This open space can represent a positive charge for us in this example. Now we have our 4-membered ring intermediate, the second intermediate. This one, again, similar to a ball and stick model. However, where it really shines is this final segment where we have the dissociation between the carbon and the oxygen and the carbon and the phosphorus. First off, this carbon-phosphorus bond is going to break and become a double bond here at the carbonyl, or former carbonyl center, in which this bond will then break with the oxygen. Again, bending this represents a double bond formation. So now we have our alkene in the Z conformer as we get in the Wittig Olefination, along with our oxygen phosphorus group with its double bond. Thank you for watching the video today. If you have any questions, always please shoot me an email, and thanks so much.